Hello there, and welcome to IQT's The Quantum Dragon podcast. My name is Brian Siegelwax, and I am the caretaker of the Quantum Dragon. My guests this episode are Ryan Laffler, President and CTO of Quantum Corridor, and Terry Cronin, VP of Business Development and QKD Evangelist at Toshiba International Corporation. Welcome to the show.
Thanks, Brian. Thanks for having us.
Okay, many people may not realize that the news often closely follows official announcements because we receive them in advance, prepare what we're going to publish, and then schedule our respective articles for after the embargoes have been lifted. And I say this because I'm about to reference pre-release communication. There were four things that caught my eye about Toshiba and Quantum Corridor's QKD pre-announcement, and my inquiries are what ultimately led to this podcast. So Toshiba and Quantum Corridor unveiled the first cross-state quantum key distribution exchange over a live commercial network. Assuming you could do key exchange over any live commercial network, what is the significance of specifying that it was cross-state? Other than simply increasing the range, would there be any difference if you connected Chicago to New York? Would there be any difference if you connected Chicago to Quebec? What difference do borders make that you specified crossing a state line?
You want me to take that?
Yeah, why don't you start us off?
Great. So a couple things. I'll answer your first question. Why this network and why not a traditional communications network? So there are a couple special properties that need to be had on a network. The first requirement is for quantum keys in general, whether using protocols like BB84 or post-quantum cryptography protocols, E911. You have to have a coherent network. And so coherent network is what enables those pipelines of communication. And there's a technology that's called D-Wave. Furthermore, our network has a technology called reconfigurable line system on that coherence. So we can parse out individual channels for customers. We used to say that we were a quantum-enabled network. So this is the second part of your question. Before, meaning that we had those table stakes to pass quantum protocols over top of the network. And now we can officially claim that we are a quantum network in that we have allowed this key exchange to take place with Toshiba's platform. And then the last question that you had was the uniqueness behind a bi-state. So there is a mileage that makes a difference on this. And that does limit distance and the points that matter. And so successful tests in lab have done this over 70-kilometer distance, which is roughly 35 miles. And so when you have points between cities cross-state, it's significant because a multi-collaboration between two different states in key exchange is slim to none, especially on commercial network in the United States. Is that a good starting point, Terry?
Yeah, and if I'll just add in that, so from a technical standpoint, there really isn't anything that would prohibit communication between any of the various states or going across state line. I think what's unique in this case that the Quantum Corridor team is doing is because most of those projects are still very research heavy, very lab related. They're largely still interfacing between a lab and maybe an outside location in that. This is unique in the sense that Illinois and Indiana, um, that greater Chicago area, looks at quantum as a holistic picture to make sure that everything that they're doing is impacting the users, the customers in that area. And Quantum Corridor is uniquely positioned with the facilities to be able to reach into Illinois.
What would be the difference, let's say you stretch from Northern California to Southern California, so it's a long distance, but within one state border. Is there any significance to the geopolitical border?
You would have to have a trusted node in between there for that type of mileage. So, we have a two node network that's available now. In order to do that, you would have to have a multi-nodal network, meaning that it's received and then retransmitted, right, in order to hit that distance. So this is the first two node network in a commercial network environment. And so to answer your question, like politically, it's a different question entirely. But what I'm talking about is purely from a space physics technology standpoint, the things that you have to hit that. In terms of geopolitical, here in the Chicago area, because I don't know much about the California makeup, you have significant points of interest here in the Midwest, such as IQMP, in the might that Pritzker's putting behind the quantum campus that's being constructed here on the lake shore. You have Purdue, which is one of the best engineering schools here in the United States, and specifically has quantum science division, and also University of Chicago, which has Chicago Quantum Exchange, which is the leading quantum program at a university here. So you have this network that passes the doorstep of those significant points of interest, and then a Z point that goes to 350 Cermak, which is really one of the largest internet exchanges in the world for porting and peering and getting out to other places on traditional comms.
Yeah, and I
I have
think just
a,
to
sorry, go ahead.
oh, go ahead. Well, I was just going
No,
to
I have
say,
a background in political science, so I'm probably the only person in quantum who would ask such a question. It just
no, and I
pops in
think,
my mind, there's a border, doesn't mean anything. But
yeah,
were
the
were
border
you going
itself.
to add anything?
Well, yeah, I think what I was going to mention is so the border in itself doesn't mean anything from a technology standpoint, from a limitation. What you have in the greater Chicago area there is you have a unique set, as Ryan was talking about, you have a unique set of assets. Those assets being um, very strong, successful universities in physics and mathematics across both states. You have infrastructure that was built out previously for industry and the coal and steel industry. And so you have a whole set of unique assets. And so the two states kind of teaming up together in this area to work together is unique, where in a lot of situations the states are pushing for funding and other uh, commitments and things from the government much more on a state only type basis. And so technology, nothing really different, but maybe a little bit to your geopolitical, seeing that in the Indiana and Illinois are working together closely on this is a little bit different. I think
Makes
you'd see
sense to
that
me.
same kind of thing in the Washington, D.C. area, but in a lot of the other communities that quantum area is kind of centralized within a particular state.
Okay, the pre-announcement mentioned that you demonstrated a real-world use case, and I'm not asking for specifics, but what generally was the use case? In other words, It's one thing to say that the demonstration succeeded, but what did the user successfully do? Did someone send an email? Did someone send a payment through a bank? What was the real world use case or the real world use of a quantumly distributed key? Who's going to be using this network?
So I can talk a little bit about that. So there were sessions that were run. So first of all, what we wanted to do is we wanted to test in real world conditions. You have the key exchange element of the network. You have the commercial traffic element of the network. So those, first of all, are distinctly different. And on the key exchange portion of this, we ran continuous sessions between the key exchange boxes over a dark fiber portion of the network. And those go through real world conditions. So those go under rails, those go under bridges, those go underwater, those go through many different types of environments and have many different temperatures that you're testing in. Obviously, approaching the Chicago winter here. And so there were things that were speculated on. First of all, that you do in lab, or you try and emulate in lab, but not quite. You can always get different results in the wild. So first of all, we did it, and we did continuous sessions. And then the second is that there's a marriage that has to occur then between the key exchange sessions themselves and the wavelengths, the Sienna wavelengths that are out there. And that's where I was talking about state of coherence and RLS FlexGrid technology to marry that up. And then that attaches to a routing engine where we take that and we channelize it. And we have a authentication that first takes place on the key exchangers. And then that gives way to the routing protocols that we build in for commercial sessions. And so, we were under pretty fierce NDAs here, so I can't talk about specific customers by name. But what I can say is that enables multiple types of use cases, and it can enable anything from security for one, and that's a big thing for financials. And it could potentially enable AI and coefficients that are created from enabling different graphics clusters and supercompute pods to talk, and you can establish pipelines for QPU traffic for coefficiencies that would be created on AI systems. Eventually, to the exchange of photonics networks that would communicate across the network for defense use cases, for terrestrial to free space networks, for defense systems, to climate modeling systems. I really could go on and on with specific use cases that this would support. But just like the channelization of anything and the IPing up of things, if you look at, for example, TDM to DWDM on networks, we thrive when we start to individually address these up for clients. And that's where it really becomes real commercial use case, in that I can say customer A, you're separate from customer B and C on your own independent sessions that are generated over this network for the use cases that we might support. I'll put that out there. Terry, you want to add to that?
I think that's pretty thorough. I think you covered a lot of it.
Great.
So the announcement said something like a use case or real world use case, but there were sessions, so really all sorts of stuff was done.
That's fair.
Okay, that's a key grammar point. Let's see. I use a network, and I generally don't think about it unless my connection fails. I've set them up before. You plug cables into ports, you configure some stuff, and then you're hopefully up and running. I am not a network specialist. So when you say no quantum specialists required, is that what you're referring to? Anybody can use it, anybody can build it. What do you mean by no quantum specialists required?
Do you want me to jump in first on that one, Ryan?
Terry, you let me know. I can take anything that you'd like.
Well, I'll start and then you jump in because I think this was one of the things that really drew us to Quantum Corridor. When you think about what's happening in the quantum space today, most of these early trials and test beds are largely that. They're test beds. There's links, a couple links one way or the other, and they're focused on organizations that have substantial resources already in the quantum space. So they've got a big R&D presence. They've got lots of people that are subject matter experts. And so for this to move beyond those environments into truly usable environments, like Ryan was just explaining, we believe QKD will end up being more successfully deployed through service providers. In the case of like Quantum Corridor, all of that back office technology, all the R&D, all of the quantum specialization and network is all managed by the Quantum Corridor team. So users can get on and actually then use it the way that they need to do, whether it's sharing data or it's video conferencing or whatever their particular use case is. They don't have to become a network specialist, a quantum specialist in order to be able to use this technology. Ryan, do you want to add anything to that?
Yeah, I mean, what we're focused on, Toshiba is a partner that enables it, is having an entire package that we take out to users. And so what that would include is almost like multiple layers of the onion, right? We have the infrastructure, which is obvious from the dark fiber to the facilities that we have the network in. And then we have the key exchange layer that I covered on the question before, then combined with the commercial network that was covered before, but then integrated with the software that allows the client to do real things over top of it. And whether that through the software platform is to set up layered point-to-points for internet exchange for places that they might want to go, or applications that they might want to get from point A to point Z across the network securely, or whether it's real use cases for, let's say that they want to fire problems over a quantum computer, which, by the way, we have a couple platforms that we'll be announcing soon live on our network. They want to solve algorithms over a platform. So then they can choose the security. So if you imagine almost kind of a menu that would have a drop down, they select the route that they're building. Is it a layer 2 leg? Is it a layer 3 leg? IPsec, MACsec. Select the type of encryption that they would like to use. So QKD, for example. And then they have a problem that they want to solve that would be some sort of algorithm they would fire at this platform, right? Which would be over top of our network. And so the future is real problems that would be solved. Global unknowns that would be solved, whether it's, a client wants to solve, a chemistry synthesis problem, a folded protein, or solve an AI routing problem or a telecom problem. There's a whole bunch of algorithms that we see that are going to need to be solved. And the last thing that you want to have is these algorithms running across a network where you do not have a quantum safe environment, right? So what we want to do is not just be the infrastructure guys. We don't even want to just be the powered by guys. We eventually want to build a platform that's powerful and provides a comprehensive solution set for customers. That way they can go run these problems that are impactful to their actual business. And so what I find is that we're one of the few that are contemplating real commercial use cases out here in this ecosystem. As Terry said, we do see that it's still very R&D heavy in this space. And so we are really, really excited about the partnership with Toshiba here, because they represent one of the final layers of the onion that are important for getting these algorithms where they need to go in a secure place to the computers that will potentially solve these algorithms.
Okay. And quote, Toshiba is proud to empower the growth and innovation of secure quantum infrastructure in the US, unquote. Overall, entanglement-based quantum networks are bigger in the US and QKD is bigger in Europe. What's the strategy behind targeting QKD in the United States?
Terry, this is a great one for you.
Yeah. Well, so I guess, if you look back to the beginning and certainly as most of your viewers understand, um, the impact quantum computing itself is going to have on security and today's encryption with things like Shor's algorithm and frankly additional ways that these computers will be able to be used to impact how people are securing their secrets today. That's going to have a huge change, and companies need to look at how to protect these assets. Now, we believe PQC is the new foundational um, basement level, right? Everybody should be upgrading their equipment to PQC today, making sure that that's now that initial, like I said, initial layer. But just like two-factor authentication or anything else that you secure, uh, your most important assets, your company IP, your healthcare records, your financial modeling, all of those type of things need a higher level security because PQC is at the base. PQC is just smarter, more complicated math to create an algorithm that's replacing today's. And so um, theoretically, that means it is potentially breakable in the future. And this is why you see such a focus in NIST and others with being crypto agile. It's kind of like we expected, just like we've expected previous generations of encryption to constantly have to be upgraded. You need to build your PQC environment to be ready to be updated. QKD is information theoretic. It's using all those same laws of physics that you use with the rest of the QIS type applications. And by doing that, that means that once you deploy that solution in a particular link, that area is secured and doesn't need to be managed as tightly as a PQC only link. And so we believe in defense in depth. We think the two work together perfectly, creating a new foundation, which raises the bar, but then to bring QKD into areas where you need that security. And so that's a lot of what the work we're doing with Quantum Corridor does is that backbone of the network creates a shared infrastructure that enables companies to be able to securely transmit in an environment that allows for multi-user and multi-tenants to keep pricing down so they can get the advantages of QKD, secured technology, but also on prices that become a little bit more reasonable for companies to implement.
My last question is not directly related to the announcement. The demonstration used existing fiber. Is fiber the future or satellites the future? What are the near-term and long-term futures of this collaboration?
QKD's been in space since the late 80s, but we do believe that it will be definitely be a hybrid. There will be need to be a lot of terrestrial to free space application that's out there, and obviously those satellite systems will be powered by photonic networks that carry QKD across them to satellite uplinks. So I think you're going to need both. That's my short answer.
Yeah, I think that the key point on the existing fiber is, you think of quantum and especially in the compute and some of these areas that you need a lot of dedicated, very costly, very difficult to manage environments. And so what we're saying in QKD is that the Toshiba multiplex equipment will work on the standard lit fiber that exists out there today that is connecting these data centers to their end users to make deploying it easier and quicker. Now, as Ryan was talking about, you'll layer technologies like satellite in to extend those distances because the limitations of being a physics-based technology are that the photons can only achieve a certain distance light length before they decohere to a point that they're no longer usable. And so a fiber backbone network with trusted nodes is how we'll first build out these city and intracity networks. But satellite will exist to be able to take you across continents. And as Ryan I mentioned earlier, there's a lot of work happening in the satellite space today in R&D to be able to link quantum corridors data center in Indiana directly to UK, to Japan, to anywhere else in the um, in the world that opens this technology. So fiber is core. Free space will improve it and be able to extend that distance.
Well, with that, I'm all out of questions. The floor is now yours to say anything else you'd like to say.
The Ryan, would you like to start, or do you want me to start?
No, go ahead.
Okay, so I think as we pointed out earlier, what's truly unique about this solution is that it can be deployed today. And the reason why today is important is because the more you look at the news coming out of the quantum compute space, we're seeing accelerated roadmaps bringing the day forward that we believe that we'll have a powerful enough quantum computer that will be able to break today's encryption. And so the need to um, do audits, to look at your systems, to understand where your risks exist is now because many countries or bad actors, industry, and others are in the process of capturing that data today and sitting on it. And so if you have a patent that has a 20-year lifetime and you believe a quantum computer can break that in 5 years, you've just lost 15 years of revenue and profits to offset the R&D investment that you put into that. Your healthcare data, that never changes. And so anything that has a long shelf life, you should be looking at next generation technologies to protect that. And you should be looking at those today to help protect against future threats to that.
That's,
Ryan?
that's yeah, that's well said. And there are technology companies that there'll be significant, yeah, many significant impacts for aside from just the security element. For example, drug synthesis companies. This could mean billions of dollars to their bottom line, having efficiencies solved by quantum computers on our platform. But again, to Terry's point, it's the data at rest that we want to protect, and the algorithms going over top of the network live, right? The other aspect to this are financial companies that are looking at time clock synchronization, right, or other interesting algorithms that can help them understand QAOA, for example, financial risk portfolios, those sort of things. So they put significant amount of money into GPU compute clusters and refresh cycles. So you're talking about hundreds of millions of dollars of bottom line, if not billions of dollars across the industry. But then you're changing from compute clusters that are at site to compute clusters that are potentially in the cloud. But then there's data. There's the very sensitive data that's going back and forth across that network. So how do you secure it, and how do you enable efficiencies through QKDs and allowing quantum computers to talk? And so, these are all the things that we're solving for. It's not just security; it's efficiency. In these use cases, and I'm just very excited to be contemplating these things and participating in these use cases with a partner like Toshiba.
Sounds good to me. And thank you very much for joining IQT's The Quantum Dragon podcast. And thanks to everyone who's still listening. There will be links in the podcast description for more information. As always, feel free to stick around for the outro music. It's called Dungeons and Dragons. Enjoy.